Hi, I'm Hiroyuki Yamamoto from JIST. I'd like to explain about our jazz harmony analysis method with epsilon-transition and cadential shortcut. As a method to give interpretations to jazz chord sequences, we studied an approach based on a model called tonal bit space. The tonal bit space, or TBS, is a music model which provides a foundation to the harmonic analysis. And with this, we can calculate the distance between two degree key pairs, which we call chord interpretations, and the connections of the two chord interpretations with smaller distance values can be considered to sound more smooth or natural for us than those with larger distance values. Based on this, we can compare the plausibility of the interpretations of chord sequences. For example, for the chord sequence CFGC, I believe almost everyone prefers the first example to the second one. And indeed, when we calculate the TPS distance, the first example's value turns out to be much smaller. When the two interpretations are within relative keys, the distance is defined as equation 1, the sum of three elements. The region is the distance between keys. Chord is the distance between degrees, and basic space is the distance concerning constituent pitch classes of each chord. The basic space is like this, but I won't go into details here. Relative keys are defined as equation 2. For the interpretations out of relative keys, the distance is defined as equation 3. It's the shortest combination of the relative key distances. TPS only defines the distances of the pairs of chord interpretations, and there has been proposed a method to find the most plausible interpretation path for a given chord sequence by Sakamoto et al. The process is as follows. Given a chord sequence, first create nodes for each chord's interpretations. In this example, each chord has 6 interpretations. Next, fully connect each neighboring node. Then set TPS distances to the corresponding edge weights. Every arrows, except for those with start or goal node, connects two chord interpretations, so there exists a TPS distance. Finally, find the shortest path from start to goal using the Viterbi algorithm. But this approach has some limitations. First, tetras are not considered. TPS considers only major and minor triads, but it is insufficient for jazz harmony analysis. Second, natural, harmonic, melodic minor scales are not distinguished. These are also important for jazz performance. Third, every chord has only one interpretation in an interpretation path. For example, for the sequence A7th, D minor 7th, G 7th, C major 7th, we may want to interpret A7th and D minor 7th are on the D minor key, and D minor 7th, G 7th, and C major 7th are on the C major key. So D minor 7th here is acting as a pivot chord. These kinds of key modulations are common in jazz, but it's impossible to interpret this way. And next, temporal direction is not considered, as it's named space. The distance on TPS is designed to be symmetric, but it seems a little strange to consider, for example, the progression from a first degree to fifth and fifth to first are identical. And also, the relations among more than two chords are not considered. For example, some chord sequences found very often in jazz, like 2-5-1, cannot be dealt directly with it. And as a result of these limitations, the number of shortest paths often becomes enormous. In this study, we propose these extensions to address those limitations. First, we extend the target chord types from just major minor triads to 8 chord types with corresponding scales and functions. This time we obtained the list from this textbook. Second, we introduce epsilon-transition to express paths which contain interpretation changes within a chord. In the figure shown here, the red and green arrows represent an interpretation path, and this green arrow is the epsilon transition. This feature enables us to express a key modulation within a chord. But if we add arrows in this manner, the graph becomes to have a lot of loop structures. Then we cannot apply Vitabi algorithm. So we change the graph a little. We duplicate every chord interpretation layer, the vertical layer, so that each chord can have at most 2 interpretations at once, without losing applicability of Vitabi algorithm. Thirdly, we extend the graph further to add new edges, which we call cadential shortcuts. This allows us to consider 2 or more chord relations with temporal directions. We referred the textbook again and obtained the cadence patterns frequently used in jazz. These are sequences of chord functions, which we have introduced in the first extension. These patterns can contain more than 2 elements and have temporal directions. Consecutive saved chord functions can be wrapped into one. So, for instance, the first pattern matches not only the sequence dt, but also ddt or dtt, or things like that. Then we discount the distance whenever these patterns occurred in the interpretation path. Now, if the path indicated by 2 red arrows matches our cadence pattern, we want to discount the distance of the path. Then, instead of discounting the weights of the red arrows directly, we add a blue arrow that indicates the occurrence of the pattern and has the weight of the discounted path. This is the cadential shortcut. We search for all the cadence patterns in the graph, and for every identical pattern, we add cadential shortcuts. This modification also retains the applicability of the Vitabi algorithm to find the shortest path. The resulting graph looks like this. We added only one cadential shortcut here, but of course there should be many. Although the graphs become larger and more complex, proposed extensions are expected to reduce the number of the shortest paths. So we checked if our approach really works. In this experiment, we used Jazz Corpus dataset, and for each music piece, we extract every successive 9 chords in the sliding window, and apply the analysis described above and calculate the averages of generated graph complexity and the numbers of the shortest paths. Compared to the original method, while our extensions increase the graph complexity, the number of resulting shortest paths is reduced a little. Next, we applied the same calculations, but this time we used the whole piece of several well-known jazz standards. Though each piece has different characteristics from the others, it can be seen that in all cases our proposed method could successfully narrow down the numbers of shortest paths at any rate. This is a concrete example of the first 8 measures of Fly Me to the Moon. Consecutive red arrows represent cadential shortcuts, and green arrows represent epsilon transitions. The result of the original method shown in Figure A contains many forks with the same cost, and in this example there are 16 paths. On the other hand, our method B could find just one shortest path. As can be seen from this example, the resulting paths typically contain some cadential shortcuts which are connected with epsilon transitions. Using this structure, we can generate a tree representation. Red lines are generated from cadential shortcuts, and green lines from epsilon transitions. In the case of A, we can see the structure in which some cadences are interconnected by key modulations. In B, all trees have just one cadence, because no epsilon transition is detected. Overall, our method seems to detect modulation sequences, which finish in either relative keys. Although the structures expressed by these trees are still very coarse, they seem to capture some basic structural facts, so we believe our three extensions, especially epsilon transitions and cadential shortcut, successfully disambiguate the result while improving the expressiveness. In the next experiment, we utilized cadential shortcuts to evaluate cadence patterns. In the foregoing section, we adopted the cadence patterns from the textbook as de facto standards, but here we dropped it and examined all bigram and trigram patterns, and also, this time, we included patterns of degrees. We used just corpus and 9-code sliding window again, but this time we replaced the code at the middle of each window with all possible code candidates, then test how frequently the shortest path passed the through code, and we observed how this frequency changed depending on which cadence pattern we used. And this is the result. This table shows the patterns by which the accuracy increased the most compared to that without using a pattern, and the patterns that decreased the most. We think this result confirms the limitations of the former approach we mentioned above. About the necessity of trigram, we can confirm that from 3 triples in this table. In each triple, the gain of trigram is larger than that of bigrams. For example, the trigram 251's gain is larger than that of both bigrams 25 and 51. And about the necessity of the temporal direction, we can confirm that from the red-colored pair in this table. While DT is among the best patterns, TT is the worst one. So, as we thought, longer relations and the temporal directions are important. So we studied a method to give an interpretation to just code sequences, and proposed some extensions to the prior approach to address the limitations. The correspondence between the limitations and our extensions are shown in this table. But our approach still has several limitations. For example, there's no distinction between long-term and short-term modulations. Values of the most parameters are not assessed theoretically. Applied code list and pattern list are not sufficient. Chords are evaluated equally regardless of their length or relationships with beats. Repetitions in code sequences are not considered, and maybe more. We think these are for future work. That's all. Thank you.
Hi, I'm Laurent Feisthauer from France, and I work in the Algomus team. The team works on high-level analysis of music scores. We like to model patterns, melodies, harmonies, rhythms, and textures. They are the first steps before working on musical forms such as fugues, variations, and sonata forms. Today, I present you my work dealing with local key estimation. First, a word about tonality. Tonality consists in a hierarchical arrangement of pitches referred as scale degrees relatively to a tonic indicated by the key name. A key also implies a scale. Each pitch has a function, the most important ones being the tonic and the dominant. Tonality implies relations between these pitches like stabilities, attractions, as well as harmonic directedness. Therefore, switching from one key to another also change these relations and the musical perception of the listener. Let's listen to the beginning of a string quartet composed by Mozart. It starts in D minor. Try to feel where the key change. You may have heard that at the beginning of the blue part, at measure 10, there is a distinct switch in harmonic expectations. We are now in F major. You could also have heard unexpected tensions at the spots circled in black. Those are called tonicizations and are really brief change of local key. They are used to emphasize a certain scale degree. Here, there is an emphasis on the G major chord with, just before it, a dominant harmony relative to this chord. Many scientists designed algorithms to identify in which local key we are on a given time slice. The most popular approach is probably the use of pitch profiles introduced by Krumenzel and Kessler in 1982. In C major, you expect to have more C, E, and G, but also other pitches as well. A pitch profile is an histogram that states the prevalence of these pitches. When you correlate pitch profiles of the score with pitch profiles for each key, you have an estimation of the global key. But for local keys, it is harder. We must choose the right window. Last year, Nápoles Lopez introduced a hidden Markov model where the pitch profiles are encoded in the emission probabilities. He also compared previous approaches on pitch profiles. There are also many other interesting approaches to model tonality, such as the tonal pitch space by Lerdahl and the spiral array by Xu. We now see the emergence of machine learning approaches. Today, I present a new approach on key estimation and especially on key changes. We want to model what there is really in music when the key is changing. What we propose is based on musicological knowledge. So, what aspects of the music make the listener and the analyst feel that there is a modulation? A first signal is when one of the notes does not match the current key. For example, here the C pitches are circled in red. Before the modulation, almost all C pitches are C sharp, the leading tone of D minor. After the modulation, every C pitch is a natural C. So, the natural C triggers the modulation by changing the scale heard. This is what we call pitch compatibility. To model this phenomenon, we introduced the current diatonic pitch set, also called current diatonic scale. The current diatonic scale is the last scale we have recently heard. Here, at bits boxed in red, C is sharp. There are no C in this measure, but the last C we heard was a C sharp. Somehow, we still remember this C sharp, and thus the current scale here has a C sharp. Listen to the current scale. Now look at the green box. Here we hear a natural C. Starting from here, the current scale has a natural C. The current scale becomes this. The idea of this current scale is that things move forward. Once you heard a pitch, you remember it and it plays a role in the tonality. How do we use the current scale? We just set a distance between a key and the current scale by computing the number of different pitches. Here, of course, when the current scale has the C natural, the key is closer to F major than to D minor. You can find more details in the paper. Let's move to another signal of modulation. Often, you have significant harmonic progressions, such as an arrival on the new tonic, or even stronger, a dominant to tonic progression in the new key. We call this tonality anchoring. At the beginning, almost all roots of chords are D or A. These are the tonic and the dominant of D major. After the modulation, most roots are F and C, the tonic and the dominant of F major. Somehow, what confirms the modulation is the authentic cadence at the end, C to F. We set a distance concerning these chord progressions. We have an heuristic to identify a dominant to tonic progression based on voice leadings. On this kind of progression, we expect the leading tone to go to the root of the tonic, the seventh of the dominant to go to the third of the tonic, and the root from the dominant to go to the root from the tonic. Let's look at the modulation point. We define a distance to model how far we are from such a progression. The details are in the paper, but look here. We have zeros in F major, because we detected a dominant to tonic progression in F major. And we also have other values for D minor, because there is no dominant to tonic progression in D minor anywhere. Our last signal tries to model the feeling we have when we switch from one key to another. D minor and F major are parallel keys. It's smooth to change from one to another. On the contrary, going, for example, from A minor to E flat major will give you a harsh feeling. Here is an example of this kind of modulation written by Weber. We also want to have a measure modeling this proximity between tonality. There are many formalizations possible that defines how one key is close to another one. We refer in this study to Weber's key relationship chart established in 1820. According to this chart, it's cheap to modulate to parallel and homonym keys, or by one position on the circle of fifths. The further we modulate, the higher is the cost. That's all. Our model is complete. We just modeled what we think what a modulation is: pitch compatibility, tonality anchoring, and tonality proximity. We just add coefficients in front of each distance to normalize and to weight them. The output of this model is a table with 42 rows, that is the number of possible keys, with as many columns as bits present in the score. We compute that with dynamic programming, and we get the tonal plan by backtracking. So, does it work? We evaluate this on 38 string quartet movements written by Mozart. Here are the results on K157. The key with the local minimum is generally the one given by the reference, mostly C major, but also C minor and G major. In the paper, we discuss how a component of this score contributes to that result. We then evaluate the algorithm on the whole corpus. With the best set of coefficients, we have an accuracy score of almost 85%. The two measures who contribute the most are the current diatonic pitch set and the Weber table. If we go deeper into the results, the algorithm shows better results on pieces in major main keys than in minor main keys. This is a non-issue in key detection. Indeed, in minor, you have floating 6th and 7th scale degrees. Results also show that subdominant keys are more difficult to predict. We also show in the paper the results for each scale degree. That's it. Looking at how key change and how modulations are performed is at least as interesting as keys themselves. We have introduced techniques to model signals of modulation, such as the current diatonic pitch set and dominant to tonic progressions identification. There are many perspectives and comparisons to be done with other methods, but definitely we feel that by modeling these key changes, we get something more than just computing pitch profiles. Thank you for your attention.
Hi everyone, I'm Minz from Music Technology Group of Pompeu Fabra University. Today I'm going to talk about our recent work, Evaluation of Convolutional Neural Network-Based Automatic Music Tagging Models. I collaborated with Andres Ferraro and Dmitry Bogdanov under supervision of Professor Xavier Serra. Before we start, let me give you a brief summary of our work. First, we revisit recent state-of-the-art music tagging models, which are mainly based on convolutional neural networks. And we evaluate those models under the same condition, such as same dataset, same data split, same computing environments, and same library versions. Also, we assess their generalization ability by giving perturbation in the input space. Finally, we provide PyTorch implementation and their pre-trained models for reproducibility. Now let's start from the motivation. Convolutional neural network-based deep architectures could firmly establish their state-of-the-art performances in many domains, such as computer vision and natural language processing. Thanks to its versatility, it is also very prevalent in music information retrieval research. These data-driven approaches lighten the burdens of the careful and elaborate feature design steps in music information retrieval. And it facilitated an end-to-end music representation learning for the given task. Convolutional neural networks are also actively adopted by automatic music tagging researchers. Many ingenious CNN-based architecture designs have been introduced, and they showed remarkable results in audio-based music tagging. The question that arises here is which model performs best for the automatic music tagging, and which model should we choose? Indeed, it was not easy to answer this question before, because researchers unintentionally used slightly different experimental setups from each other when they report their results. For example, some of the papers use different dataset and different data splits. And some of them use different data preprocessing. They discard songs without any tag, or discard songs with short audio length. Furthermore, each model uses different optimization techniques, which can be sometimes more critical for the performance than the model architectures. Also, each model was experimented in different computing environments and different library versions. So our motivation is very straightforward. Let's reproduce all of these models and do the evaluation under the same condition so that the following researchers to choose appropriate models for their future research in automatic music tagging. These are the models that we investigate in our research. I'll briefly introduce the characteristics of each model in terms of architecture design. Fully convolutional network is a variant of convolutional neural network that consists of only convolutional layers without fully connected layer. Fully convolutional network for music tagging consists of 4 convolutional layers, and each layer comprises convolution, batch normalization, rectified linear unit, and max pooling. To cover 30 seconds of audio, the network uses wide strides for max pooling. Musicians try to interpret music tagging as two steps, front-end and back-end. Front-end extracts relevant music features, and back-end temporally summarizes the extracted features. For the front-end of musician, the authors used musically motivated filters. Vertical filters capture pitch-invariant timbral features, and horizontal filters capture temporal energy envelope of the audio. Finally, the extracted features are summarized using one-dimensional convolutional neural networks. Sample-level CNN tackles the music tagging in an end-to-end fashion. It takes raw audio waveform as its input. The model is one-dimensional convolutional neural network with 11 convolutional layers. And its variant improved the performance by adding squeeze and excitation blocks in each convolution layer. Convolutional recurrent neural network for music tagging try to interpret music as a sequence. It extracts short-time audio features with CNN frontend and summarized them with RNN backend, which showed its ability of sequence modeling in natural language processing. Self-attention-based music tagging model was also proposed to model music as a sequence. Instead of RNN backend, it uses transformer encoder, which recently reported breakthrough results in natural language processing. Since it uses stacked self-attention layers, the model is interpretable. Harmonic CNN takes advantage of trainable bandpass filters and harmonically stacked time-frequency representation inputs. This harmonic tensor preserves spectrotemporal locality while keeping the harmonic structures through the channel. Short-chunk CNN is a prevalent two-dimensional convolutional neural network with 3x3 filters. Sometimes it is also referred to as Vujicic model. It is similar to fully convolutional network, but it uses short audio chunks as its inputs. Hence, it uses more dense stride for max pooling layers. We call this short-chunk CNN to prevent from making confusion between full-length audio-based approaches. We also experimented short-chunk CNN with residual connections. This table shows input length of each model. As you can see from the table, fully convolutional network and CRNN and self-attention-based model use long sequence of audio, while other models only use short audio excerpts for multiple instance learning. In our experiment, we used 3 different datasets. Magnetic-attuned dataset is one of the most broadly used dataset for music tagging research. The dataset consists of 26,000 pre-listened audio with manually annotated tags. For the scalable research, previous works commonly tested their models with the million-song dataset. The million-song dataset contains 242,000 pre-listened audio with crowdsourced tags from Last.fm. And we further evaluate music tagging models with a relatively new dataset called MTG Jamendo dataset. MTG Jamendo contains 56,000 audio tracks with Creative Commons license. Hence, it has full-length audio tracks different from other datasets. Tags are provided by the artist, and then the tags are cleaned by the creators of the dataset. For all of these 3 datasets, we only used top 50 tags following previous works. This table shows the experimental result. Overall, harmonic CNN, short-chunk CNN, and short-chunk CNN with residual connections consistently outperform other models in 3 different datasets. Musician, sample-level CNN with squeeze and excitation, and self-attention-based models also reported competitive results, but performance of musician went lower with larger dataset. Since fully convolutional network, musician, and CRNN used 96 melvins in its original implementation, We also tested them with 128 melvins like other models for the fair comparison. However, we could not find any significant differences. Note that these models were optimized with 96 melvins by the original authors, so this is not the best of 128 melvins. To further investigate models' performance, we assessed their generalization ability with input perturbation. We deformed the input audio and observed their performance after the deformation. 4 different deformations are applied following previous data augmentation research: pitch shift, time stretching, dynamic range compression, and white noise addition. As a result, harmonic CNN showed the best generalization ability except for the heavy white noise addition. And short-chunk CNN generalizes the best against heavy white noise. Musician could generalize well, but its musically motivated filters could not generalize against pitch shift. And dynamic range compression is not critical for the prediction. So here's our conclusion. Models with short audio excerpts, such as short-chunk CNN and harmonic CNN, show the best performance. This means sequence-based models with longer audio inputs need to be improved more. Harmonic CNN shows better generalization ability than other models. Since it keeps harmonic information through its channels, it seems to better generalize than Mel spectrogram-based models. Musician is beneficial for a relatively small dataset, but assumption-free models can scale better. We could not find any significant performance difference between raw audio-based models and Mel spectrogram-based models. Finally, for reproducibility, we share our codes and pre-trained models on our GitHub repository. Thank you for your attention and hope to see you soon face-to-face. Stay safe.
Let's go. Okay. Hey, so hi everybody. So I'm Jean Bresson. I'll be the moderator for this Q&A session. So first, thanks to the presenters for such interesting works and presentation, and thank you everyone for following us online. So it's actually nice to have a session with such kind of related topics, and I guess this might allow us to, beyond the specifics of presented works, also think about different approaches in systematic musicology. So I'll first try to go through the question from the YouTube chat. Please also, for everybody's following us, feel free to keep posting questions, and if we have time, I can also bring them up still for this Q&A session. So the first, let's go in the order of the presentation. So we have some questions for Hiroyuki first. The question is, how big of an impact the choice of distance between keys and distance between chords have? So could the analysis change drastically by weighting one above the other?
Yes, I think TPS has 3 distance functions for relative keys, and those weights are all 1. I think the question is about the weightings of this. But in this study, we just used the default setting and haven't investigated the impact of the parameters. And as we list it as limitation number 2 in the paper, it can be the point for our future work.
Okay, thank you. I'll ask a question after maybe. So I'll follow up because I see there are some questions on the chat coming up. The next question is for Laurent. It's about key changes. So the question is, how do you differentiate between real key changes and tonicization?
So we don't really make the difference between real key changes and tonicization. You can have more precision. You can orientate the model to detect more tonicization by lowering the weight associated to the tonality proximity measure. But we don't really make the difference between the two kinds of modulation.
Okay, and we have another question from Marco Link, which is, did you use any cross-validation procedure to compute the accuracy scores?
So at first we tried to do a cross-validation procedure, but the problem was that the order of magnitude for each coefficient is not the same. For example, for tonality proximity, the optimal weight is for Mozart string quartet is 4, and for tonality anchoring is 0.0016. So we mostly use the corpus as a test set and try to a lot of triplets for the value of coefficients. So this is left for further work to have a nice cross-validation procedure, but yeah, the main reasons that we haven't done nice cross-validation is because of the order of magnitude of the coefficients.
Okay, thank you.
You're welcome.
So next we have a few questions for Minz.
Yep.
The first one is from Sebastian Rebecki. Do you think that by using even larger datasets would improve the performance of end-to-end models like sample CNN, maybe over perform spectrogram-based models?
Yep, I think it's a really good question, and I was super curious about this as well. So I tried this for several scalable datasets, but by far spectrogram-based approaches work better than sample-level CNN or other raw audio-based approaches. So, for example, if we visualize learned filters in the sample-level CNN, they are a bit noisy. So from this motivation, there became some papers like SyncNet to learn low-level audio features in a more efficient way. Also, harmonic CNN showed that the domain knowledge can be still helpful for more generalizable audio representation learning for current scale of dataset. So I don't know how big data is needed for end-to-end raw audio-based learning, but like if we can get infinite amount of data, probably there's a possibility that this raw audio-based approach can outperform spectrogram-based approaches. But by far, for available size of the dataset, since music is especially really complicated data, I think domain knowledge-based or other spectrogram-based approaches outperform sample-level-based approaches.
Cool, thanks. The next question is also from Marco Link. Did you also experiment with relative self-attention, as in Magenta's music transformer?
Okay, as far as I know, Magenta's music transformer is symbolic level approach. If I'm wrong, please correct me, but as far as I know is symbolic approach. But for this self-attention network for audio spectrogram, it uses self-attention and it has positional encoding in it to model it as a sequence. But when I try to do some interpretable research, I could not find it is modeling the information as a sequence. But since the music is a sequential information, I'm still interested in this sequence modeling using transformer-based approaches. And also recent advances in wave-to-back or its variants prove that audio can be modeled using these transformers.
Okay, thanks. And another question for you from Simon Tyrrell is, would you say that the CNN models the human sound and music perception accurately?
Okay, actually, I also want to complain about CNN, not in terms of the performance, but its characteristic. So in the field of computer vision, they show that CNN is biased towards the texture. So it more concentrates on the texture of the information rather than like entire shape of the image, for example. And this can be applied to music as well. So like, I believe current music representation learning using CNN-based approaches, it is very biased towards texture. Sometimes like it can be, the counterpart can be timbre of the music. So I believe it's very biased toward texture. So it can model some keys or other rhythmic information. So I think that's the reason why people use other input representation for the cover song identification, for example.
Okay, thank you. So we have no more questions from the chat, but I have a few comments or questions myself. I would maybe roll back to the first presentation and ask Hiroyuki maybe a little bit more broad question about your approach. So I like the last phrase of your paper is maybe this would lead to a deeper understanding of jazz harmony. And so I'm wondering, so here you're presenting a lot of very nice models and numeric distance. What do you think you really understand more of jazz harmony from all this new information you get from it? Do you have
I'm sorry, I couldn't quite understand what they asked.
Sorry, it's kind of a wider question about, okay, you give us some more accurate graphs of how the harmony goes onto in a jazz tune, for instance, with your model. Is there some specific thing that you think can help us better understand jazz harmony from this?
From this model?
Yeah.
Yeah. No, no, I'm sorry, I can't understand.
Okay, shall I? I'm a co-author. It's okay.
Okay.
Yes. Yes. Such kind of numeric addition, that is the simple linear addition of the three parameters by the rating. And of course, this does not reflect the jazz intuition correctly, I think. And curiously enough, someone asked us that the original tonal pitch space, the author Fred Lehr said that we don't need a weighting. Just simple addition of the three parameters enough. But in jazz case, I don't think so. In classical cases, the theory is quite rigid and restrictive, so that the classical intuition is really represented in tonal pitch space. But when we apply to the theory to jazz, we need some, sensitive, a bit adjustment of the parameters, that's the weighting for the original three parameters. So we need to explore more about this direction.
Mm-hmm. Okay.
Have I answered your question?
Yeah. I mean, it was kind of a broad, a little bit not provocative, but broad question about the general knowledge we can take out of this systematic approach, not only yours but also the other approaches we've seen in this session. Another thing that interested me in this session is the difference between some formal and systematic approaches, as we have seen in the first two papers, and the more neural network kind of based approach. Does anybody has a take on how much would such harmony, key detection, modulation detection work with neural networks, or would it not work? What's your take on this?
To us?
Yeah, for instance, or anyone, right?
Yeah, of course we should take into account the neural network. Of course, we are originally treating the n-gram model, that is some Markov model, that is several sequence of course. What can be expected from these kind of n-grams? And of course, that is a kind of the convolution network or some long short-term memory model can be applied. And that is another future direction, I think. We have not considered yet, to be honest.
Okay. We have another question coming up here. Since all other information such as keys, rhythm, and lyrics are all in a raw audio spectrogram already, we need to design a music. Whoa, this goes fast. Music
sorry, it was my answer to the question from Simon.
Okay.
Some additional comments to Simon.
Yeah. Okay. Great. So I guess we have no more questions from the chat, and it's almost time for us to pass over the mic to the next session, I guess. So I will just thank everybody again and wish you all the best for the rest of this conference.